Hi, I'm Antonio Sala, and in this video we are going to give some notes on why the computations we did in the previous video on confidence ellipsoids and confidence rectangles would be wrong if we used a non-diagonal covariance matrix. If we remember, with this diagonal covariance matrix, we had these axis-aligned ellipsoids as equal density contours, and then of course the smallest area regions for a given probability, for a given confidence, will have this shape, and this is the 90% confidence case, and we have the ellipse computed with chi-square formula, the plus minus 1.96 standard deviations computing the marginals, the pink stripe going to plus minus infinity in the non-considered variable, or the greenish cyan stripe, and multiplying those probabilities, we obtain the light pink 90% confidence rectangle 0.95 square, and if we wish the 95% rectangle, then we need to expand to the dark pink one, and in fact if we expand until the confidence rectangle, let's say, is tangent to the confidence ellipse, then ellipse is 95% and the green rectangle is 97.15%. So now let us consider what will happen if I use a non-diagonal covariance matrix. In this case, this is a 2D normal variable in which the marginal variables x1 and x2 have some covariance, some non-zero correlation. And in fact, if we consider this quadratic form, this will be an ellipse, but the ellipse will not be aligned with the axis. Here we have the contour plot, and in fact it can be shown from geometric argumentations that if I diagonalize the covariance matrix, then the length of the axis is proportional to the square root of the eigenvalues, and the directions of the axis of this ellipse are given by the eigenvectors. So for instance, the large eigenvalue is 0.3, 0.95, this 0.3, 0.95, and the perpendicular one minus 0.95 plus 0.3 is this one associated to the smallest axis. So these directions will be important in the equal probability ellipsoids, and in fact, as they diagonalize the matrix, they convert the correlated normal variables to another representation in which the covariance matrix is diagonal, uncorrelated, and that representation is called principal components, which graphically would be making a change of variable. So this blue axis I drew here were just rotated to be axis aligned. Then that change of variable is called the principal component computation, and the resulting analysis from that new covariance matrix is called principal component analysis. It's an important tool in multivariate data analysis, but it's not, of course, in the objectives of this short video. So once we understand the shape of this region, then what happens with the computations we did if we repeat the code to compute this kind of plot? Well, the thing is that some of them will be still correct, but the rectangle ones, for instance, will be wrong. So it is still correct, the marginal analysis. The square root of the diagonal times 1.96 will give me this correct 95% confidence interval on x2, because the marginal analysis is, forget about other variables this x2 could be correlated with. Then we forget about everything and we compute the confidence interval. The confidence interval, marginal confidence interval for x1 will also be correct, and the ellipsoid chi-squared computation, it can be proved that it is also correct. So good, good, good. But however, the probability figures for the rectangles will be wrong. Why? Because, for instance, we computed the probability of the light pink rectangle as 0.95 squared. We say that if the probability that x1 is in the pink stripe is 0.95, and likewise the same probability for x2 in the greenish cyan stripe, then the probability of x1 in the vertical stripe and x2 in the horizontal stripe, so the probability of the light pink rectangle, would be the product of the probabilities. And then that's the wrong assumption, as the variables are not independent, they have correlation, and then the probability of the joint event is not equal to the product of the probabilities. So this figure is wrong. And as we did the same assumption in order to compute the rest of the confidence rectangles, then all these figures are wrong. So you should not execute the code for non-diagonal covariance matrices. In order for analogous computations to be valid, then you should first rotate the ellipse so it is axis aligned, and then your computations in the principal component coordinates would be okay. Or equivalently, instead of rotating the ellipsoid, we could somehow think on rotated rectangles. So the green rectangle, let's say, would end up having a shape like this, and of course another different dimensions. And then if you worked with this kind of rotated rectangles, in that case we could repeat the computations of the probability of them and be correct. But of course that needs the change to principal component coordinates we are not doing here, because okay, that would require separate videos on principal component analysis, but then as we are not doing that change of variable here, then it means that the code for the probability of the rectangles is wrong in this example. And this is why I stress here in the comment that the code is not valid for that case. So with this remark on the correlation, we end the video here. Thanks for watching.